Hi and welcome. This is the memory optimization module. In this module, we will be taking a look at how to monitor and manage memory and overcommitment of memory in a vSphere environment. We'll be taking a look at the memory concepts as well as what tools we have available to monitor memory in a virtualized environment. So memory is another key resource to ensure we have not overcommitted so that the reclamation of memory isn't so great that it's causing performance issues. In fact, one thing that's pretty useful when it comes to monitoring memory, you want to find if there's any memory reclamation happening because that is a clear indicator of a shortage of memory. So let's take a look at how we can monitor for this. There's basically two lessons here. First lesson describes memory virtualization concepts, and the second lesson is the monitoring lesson, followed by a lab exercise to demonstrate how to monitor for memory usage. So in our first lesson, we're going to take a look at memory virtualization concepts, and here we'll have you be able to describe how memory is used in the virtualized environment, explain each memory reclamation technique, and how to explain how memory overcommitment affects performance. So first things first, one thing to know about the way how the ESX server manages memory, it is essentially a multi-layer memory management model. Effectively, what the VM kernel hypervisor is presenting to memory, how the hypervisor presenting memory to a virtual machine is a lot like how a guest operating system will be presenting its memory to its applications. So the guest OS presents virtual memory to its applications. The hypervisor presents physical memory to the VM. And when we say the hypervisor is presenting physical memory, keep that in quotes, right? Physical memory, because as we all know, when there's any kind of memory reclamation, that basically means there's some kind of paging activity going on, where then what one layer thinks is real memory, another layer that's managing it may actually combine memory with disk access. So much like how an operating system will page out applications in the Windows pagefile.sys or into a Linux paging or swapping partition, the VM kernel can do the same to the VM by having the memory in the VM swapped out to the swap file. So we want to be able to measure this. Is there actually paging activity happening at the ESX host level, or is there paging activity happening in the guest level? Those indicate quite different things usually. So things also to note is that memory management in the guest can sometimes be pretty transparent or even invisible to the hypervisor. For example here, we have memory allocation requests are being mapped into the guest OS memory space. That's going to basically move pages off of the guest's free list over to the allocated list. Now, the VM kernel can see that because any kind of memory allocation request coming from an application, which will be mapped in guest OS space, will be also mapped at the ESX host memory space. So allocations are going to be recorded at the host level. However, when the guest OS frees a page, maybe the application is no longer running, the page moves back from the guest OS's allocated list over to its free list. That isn't going to be advertised that happened to the VM kernel. So the VM kernel may not actually always keep an exact accurate count of all the memory allocations that are in the guest. Some have actually been freed up. The VM kernel needs to be kept up to with this information, and we can do that. There's other techniques that are involved in doing that. It just isn't being done by the guest OS automatically. So with regards to memory management, you've got this multi-layer model. The applications will do memory allocation requests. That will map it into the guest OS, and the guest OS will then have to map that to the hypervisor. The guest OS actually does not explicitly allocate memory, though. Memory is allocated on the VM's first access to memory, regardless if it's a read or a write. But then when the application no longer needs a page, it can then be moved over to the free list, and then it basically moves over to the free list, but the VM kernel never gets informed of this, and the memory mapped page at the host level basically becomes idle. In fact, it will become what we could say stale. The VM hasn't accessed this page in a long time. I mean, think about it. The guest OS knows about all the memory allocations because it knows which applications made all the different allocation requests. The hypervisor, on the other hand, only knows that the pages belong to the VMs, and then that's it. So the guest has a far more intimate knowledge of the different memory pages mapped out in the guest OS space, where the VM kernel's hypervisor only knows that the pages belong to the different virtual machines. And then the VM kernel basically tracks when was the last time the page was accessed by the VM. If it was accessed in the past minute, the VM kernel considers that's an active page. If the page has not been accessed in the past minute by the VM, then it's considered an idle page. And so that might happen when an application is no longer running. The application mapped page, say for instance, we have this map page, this maroon burgundy page, may no longer be mapped by an application. So it's basically been sitting in the OS. It may actually move over to the free list, but the VM kernel never gets informed that the application is no longer using it. So the VM kernel basically seeing this page has gone idle. So we need to be able to have a mechanism to try to reclaim memory so that we can efficiently move memory managed pages from, say, one VM to another, right? We want to be able to promote high consolidation ratios where that there may be multiple virtual machines that, if you add up all their memory, could conceivably be greater than the actual physical memory on the host. I mean, that's just one method or one reason behind reclaiming memory. Generally, we don't really recommend, if you want to make sure that you never have to worry about memory management at the ESX server level, you could ensure that the VMs altogether add up to an amount of memory that is less than how much memory is actually installed. Here, where we've overcommitted host memory, right? We've got more memory in the VMs than there is on the host. But that may not be a big deal either, because if the VMs themselves have not allocated all of their configured memory, then they may actually have not overcommitted the server, right? If these VMs are all 2 gigabytes each and the host only has 4 gigs, well, right there we know that's 6 gigabytes of memory trying to fit in a 4 gigabyte host. But if each one of those VMs are actually only using 500 megs each, well, then they're fitting in the ESX server just fine. So you can overcommit what's called configured memory, which is what we have here, right? That's what we've done. We've overcommitted configured memory. What we may not have overcommitted, though, is what is the active memory, because you never want to overcommit that. Maybe the VMs are all configured for 2 gigabytes, but they actually are actively only using 200 megabytes each. So that's 600 megs that the VMs are actually needing. We are not overcommitting that. We've got plenty of memory for the active memory, but we've overcommitted the fact that each of the VMs are configured for 2 gigs each, which of course is 6 gigs on a 4 gig host. If you've overcommitted configured memory, that's not a big deal until you start overcommitting their active part of their memory, which is usually a small portion of their configured memory. So in the end, an ESX server is going to be able to track several elements of VM memory, but it may not be able to track as intimate knowledge about those memory pages. Say, for instance, you give a VM a gig of memory. That's your VM's memory size. If that VM's 1 gigabyte of memory is allocated, well, maybe we'll have 1 gigabyte memory configured, but maybe the VM only allocated 600 megabytes. So the VM has allocated 600 megs, and therefore 400 megs are still free. The ESX server will see that. If the VM has never allocated its 400 megs there, the VM has now been divided into kind of two categories, 600 megabytes of allocated memory and 400 megabytes of free memory, or unallocated. Now, amongst those allocated memory pages, the VM kernel can pay attention to how much of those allocated pages are active and how much are idle. The pages that have been accessed within the past minute are considered the active pages. The pages that have not been accessed in the past minute are considered idle pages. So maybe those 600 megabytes, 200 of them are active and 400 are inactive. So now we have an interesting kind of comparison here. The host will see 200 megabytes of active VM memory, 400 megabytes of idle but allocated memory, and then 400 megabytes of unallocated memory, right? That free memory that the VM never allocated. The problem is that how does the ESX server's VM kernel know that those 400 megabytes of idle memory are still allocated? It doesn't. That's the issue, right? Why is the VM no longer using those 400 megabytes? It could be that the applications are no longer using them. It could be the applications actually have stopped, so those pages actually should be moved off of the ESX server and moved into a free list on the ESX server level. Because the VM isn't going to actively tell the VM kernel about the fact that these pages should be freed up, the VM kernel can't really tell the difference between what are idle pages and actual free pages. All right? The VM kernel does have a helper here. It's called the balloon driver, which we'll take a look at in the next section. So let's take a quick break, and we'll take a look at those memory reclamation techniques that are available in the system. So we'll see you in a few minutes.